Hi, good day everyone. It's Elias again. Welcome back to Midnight Simplified. And in today's video, you're going to be learning how to write smart contracts using Compact on the Midnight blockchain network. Here are some things we're going to be covering in the video. First up, we're going to be covering what primitive data types are in Compact. Next up, we're going to look at how to define custom data types in Compact. After that, we'll move to learning what ledger states are, how to declare ledger states or Compact, and then would move on to also learn what constructors are in Compact. And after that, we'll go on to learn what circuits are. These are the most common words you hear among people discussing about Compact. ZK circuits precisely. So we're going to uncover that in this video. And after that, we would move on to what witnesses are. Why do we have witnesses and how do we use them? And next up, we would get to learn a very important aspect of Compact code design, which is called modularization. How you can modularize your Compact code so it's much more readable and manageable by yourself and other developers. And lastly, we're going to learn about specific standard library circuits that are provided to us. These are not circuits we define ourselves. These are the ones that are provided to us by the Compact standard library. That allows us to perform a lot of functionalities, like maybe receive token into a contract, send token from a contract, and maybe hash whatever values we want to hash. So that's basically what we'll be covering. And without wasting much of our time, let's dive in. Yeah. First off, it's very important that we understand what smart contracts are. If you're not new to the concept of smart contracts and the likes of that, then you can move on to in a section. But if you're just getting started with what smart contracts are and you're moving into Web3, it's important that you kind of understand what smart contracts are. So smart contracts are more like a piece of code that kind of implements business logic and the conditions that guide them. And one special stuff about the smart contract is they are self-executing. They execute as soon as these conditions are met, which means you don't need a third party. And the most important part of them is they are immutable, which is why I tend to look at them as unbreakable promises. So that's what smart contracts are. A piece of code that implements business logic and the conditions that guide them. And they are immutable and also self-executing. So a very good analogy to kind of understand what smart contracts are is for you to think of smart contracts as a vending machine. You know, with vending machines, you place a specific coin of a certain amount into the vending machine and then you select an item and then you get that particular item as far as you've provided the correct amount. So that's what smart contracts are. Now that we're familiar with what smart contracts are, let's dive straight in to writing our first smart contract on the Midnight blockchain network using Compact. So to do that, I'm just going to open up my terminal and then I'm going to quickly create a new folder inside of my Midnight tutorial directories. I'm just going to do mkdir and then I'm going to call it Midnight simplified learn compact. Don't mind me, I'm not so creative with names. So I'm just going to hit enter. And now that I've created that folder, I can cd into the folder. And then I can quickly run npm init-y. Now this helps me in initializing a new package.json for the project. And I'm going to hit enter. Yeah, it's created the package.json. And then what we want to do is open it in our code terminal. So I'm going to run code, but in our VS Code environment. So now it's opened in VS Code. Yeah. So in order to keep the project more coordinated, I'm going to write each of the teach each of the concepts in a particular um order. So I'm going to create a source folder here, SRC, and inside of this source folder, I'm going to create a first compact file. I'm going to call it lesson1.compact. Yeah. Now that I have this folder, let's dive into where I'm writing our first smart contract. So at the top of every compact file, the first thing you want to do is define the language version. This is more common with any programming smart contract programming language, even in Solidity and the likes of them. So to do that, you're going to write pragma language version. I already have the compact extension installed, and if you don't have that, you want to check the previous videos I've created in the series where you would learn how to install the compact extension for VS Code. And once you're done, you can come back to this. Yep, let's keep going. So I'm going to say pragma language version, and then I'm just going to say greater than or equal to, because I want it to only compile using this specific language version. So I'm going to say 0.19.0.0. Now this it means this compact code is going to only be compiled with this specific language version, and this also has implication on the version of the compiler that can compile this code. In order to compile this code, you need to be running 0.27.0 version of the compiler to be able to compile this compact code. I also have created a video for that to install and that particular version of the compiler. So do well to watch that if you find any difficulties. If you've already done that, let's keep going. Now, introducing primitive data types in compact. So I'm just going to write primitive, data types. So in just like every other programming language, there are specific data types that we have in compact. Like every other language, we have Boolean. So what this Boolean allows us to do is to either define a truthy or a falsy condition. We also have we also have the ability to define strings in compact. And to define a string, what you can use, there are two ways you can do that. And use an opaque data type, an opaque data type, whatever it's pronounced like. I prefer to call it opaque. So an opaque data type, and inside of it, you want to put this apostrophe sign here that you always use for defining string literals, as in any other programming language. And then you want to specify either string or you can another type, and then that is called so here it's called uint 8 array. So uint 8 array. So these are the two types of strings you can define in compact. For me, I prefer to use this a lot. If I'm going to define a byte array, I'm going to directly use the bytes primitive data type. That brings us to byte primitive data type. Now, the bytes primitive data type, this is how it's defined. So you can specify a byte of its a specific length. Say maybe if byte 5, which can be used to either represent a word like hello. It has 5 characters. What actually is a byte? A byte is more like a unit that can be used to represent a specific character or a pixel or color in majorly programming languages, because your computer cannot actually understand when you type hello to your computer, it actually does not understand that. So each of these, the hello consists of several characters. So we have HELLO. Now the computer is only able to kind of convert this, the language converts it into bytes, and then that bytes then it's converted into bits, smaller chunks, which are called bits. Usually a byte consists of 8 bits. Yeah. Which bits are usually ones and zeros. The bytes could be any number. To demonstrate this, I always like to use this chart here. You can see A is equivalent to 65. This particularly is a byte and consists of 8 bits, 0, 1, 0, 0, 0, 0, 0, and 1. So that's it. I'm sure at this point you get it. Most times you get to see people defining bytes as byte 32. Yeah. So we have bytes. We've defined 3. You have booleans, opaque data types, and bytes. Yeah. And next up, we have a way to define numbers in compact, but as opposed to the usual way you define numbers in JavaScript. JavaScript is a lot much more loose. I would say with TypeScript is a bit better, which most people actually liken to compact. And to define numbers here, you use this particular primitive data type. We call it uint, and let's specify a boundary for it. So uint, for instance, uint 32. Now, uint 32 means this uint here means it's an unsigned integer. An unsigned integer. It's different from it's different from the normal integer that we use in JavaScript. It's more similar to a big int in JavaScript. You know, in JavaScript we have several data type, and in TypeScript as well. It's more likened to this, which means that decimal points or floating numbers are not allowed. Floating numbers are not allowed. That means if you're going to use floating numbers, maybe define the specific amount of a coin, say maybe 5.25 USD, something like that. You have to find a way of scaling that number. We also have vectors. Now, vectors are a way to define an array, but unlike an array in every other program language that just goes, you have to specify a boundary for it, like a length, a fixed length array. Think of vectors as a fixed length array. I can say vector of fixed length, maybe vector of length 2 can only have a max of 2 items, and then I can also define this type of the item. Maybe bytes 32. Right? So vectors are a fixed length array. I can increase this maybe to 100. So I'm saying with this, when I define a variable and add this as the type of that variable, it means I'm saying, okay, create an array for me of fixed length 10, and the only items that are allowed inside of that array are bytes. This is why it's a lot similar to TypeScript, but of course it's not TypeScript. Yeah. So we have bytes, we have vectors, we also have lists. So a list is more like used to define an array of any length. So I'm saying in this case now, create an array that doesn't have a fixed length, and then this is the item, the kind of item I want to be inside. I want to have a bytes array that is of unlimited length. So you get, these are the basic data types we do have for primitive data types that we have for compact. And that brings us to the next version of the course, which is custom data types. So I'm going to create a new folder for that. Lesson 2. It's compact. And inside of this, I'm also going to just copy this from here. And then I'm going to paste this here. Yeah. So now for custom data types, these are data types that you get to define their actual structure, their architecture. So for compact, the two types of custom data types that you can create include structs and enums. These are the two types of data types you can create in compact, custom data types particularly. So so I can create an enum and call it maybe a status, somebody's marital status. So let me even be more explicit. Marital status. And then an enum can take two properties, and it can take more how many. It's more like a tuple, right? That you have also in TypeScript. It's more like a tuple, and then you define the specific conditions. So maybe I can say married or single. So this is an enum here. We can also see that in the compact guide, just in case you get lost at any point or you want to go through it by yourself. You can also see we have structs here. These are defined, these are custom data types. And yeah, you also have enums here, just like what I'm doing. So you can define an enum and say, okay, I have marital status, either married or single, or, or let's say complicated. Yeah. Then the other type of custom data type you have in compact is a struct. Now, most of the time when I think of a struct, I think of a struct as an object like we do have in TypeScript. So maybe this could be a user object. So think of structs as objects, and then I can call this. If you notice one thing, just to state this, if you notice at the end of most of my lines of code, I'm adding this colon. This is very important with compact because if these semicolons are not here, your code is not going to compile. You're going to get a compilation error. Of course, TypeScript is so gracious that it's going to tell you in your terminal and say, okay, this is not correct. It's expecting a colon, but it got a semicolon, but it got something else. So if you don't put this, it's just going to keep on reading on to the next line. For structs, you don't have to add it, not necessary, but you could if you want to. So for example, now I'm defining, like I said, think of structs as objects. I'm defining a user object. Maybe this would have a username, and then this would be a byte 32. It's like this is what you see a lot of people use. And think of it more like objects, keys, and values. So I can also, do add an age property for this structure and say, let's call it, it's a unit of type uint 32 as well. So this is it. You can use commas to separate them, or you can use a colon like this as well. I prefer to use the colons. Yeah. So this is an example of also a custom data type. It's called custom because we get to define how it looks and how it's structured inside of it. Of course, these custom data types can also make reference to other structs itself, or maybe enums. For instance, here we could have status. Yeah, let's call this, let's say marital status as well. Marital status. And then we're going to make reference to this, yeah. So this also is allowed in compact. And we can also reference other struct itself. Maybe still, for instance, we have another struct called an address. I like to use capital letters when I'm defining structs, so I kind of can tell the difference from which is which. So maybe the person's address has maybe let's say a location. Location. Okay, let's just say latitude and longitude. So I can say latitude of instead. Okay, you can also specify larger units. This is the highest value of an unsigned integer, you can define in compact. I can add longitude. Maybe that's a mu into 132. 128 rather, sorry. So now we can make reference to this struct inside of our object, say this person's address is of type address. This address structs that we've defined up here. This is why a lot of people liken, even including myself, liken compacts to TypeScript as well. So you can see I've defined custom structs here using this. Now, one thing I forgot to mention was if you add these numbers, these fixed lengths into unit variable, it means there's a highest number of value that's possible for that particular field that you defined with that length of an unsigned integer, and that's always calculated by 2 raised to power n, 2 raised to power of n, then minus 1. So if I'm saying a u into 128, it means I can say 2 raised to power of 128 minus 1. And that's going to give me a very large number, which means I can store a very large number inside of it. Now, one also important primitive data type I didn't state here was field. So field is a data type. It's more like a folding unsigned integer. Think of it as a uint that folds. If it reaches the maximum number, it's going to fold and start again. You get? So that's what a field is. Yeah. So, and I also have a few data types that I'm just going to copy this. That's much more used in it's not most commonly used in many programming languages. Of course, we have them in TypeScript as well and in some other programming languages, but they are mostly used in smart contracts. This includes mappings and sets. So lesson 3, I'm just going to paste that code from the previous lesson. And then we're going to talk about mappings and sets. Now, what's a mapping? Think of a mapping as a hash table where you get to store key value pairs inside of it. More like, I think I have an illustration for that here. So think of mappings. Yeah. In TypeScript, you define a map like this. It's more like it's an array. Think of it as an array of key value pairs. A way for it can store an unlimited length of data inside of it, but it has it's more like an array of smaller arrays that has key value pairs. Now, one thing you might be considering is how is this mapping able to tell which one comes before which? So it has more like a pointer, or should I call it a reference point? So it's able to tell which is placed inside of the mapping after which at any point in time. So mappings are used to keep track of maybe you can use them to keep track of a whole lot of things on chain. You can use it to keep track of, say, for instance, a list of users, right? But now you are keeping something as well in addition to it to track that user, more like an ID for the user as a key and the user itself for the value. So to define a map in Compact, you can do map, and then you add this angle bracket. And first off, you want to define what the type of the key is, and then what value you want to store inside of it. So for instance, if you're using IDs to maybe identify your users, let's say we are creating a mapping to store users, right? So we might want to say, for instance, we want to even store their addresses. Let's use something practical with blockchains. Their addresses to the user itself, right? This is not how you define it, but I'm just trying to make an illustration, right? So in this case, the address is the key and the user is the value that we want to store there. So what I can do now is say, okay, the address is going to be a byte, of course, since that's the most, that's the way we define strings, mostly in compact. So it's going to be a byte 32, and then we can say the value that we want to store is this user struct here. Now, looking at this, what you will notice is we've defined a mapping. So we are saying we are defining an array that has several smaller arrays inside. Now, what these arrays contain are a key for addresses as addresses that maps to a particular user. So that's what mappings are. Now, as opposed to mappings, sets are just they are similar to mappings, but then they do not contain key value pairs. They just contain think of them as another way to define arrays again in compact. Just an array storing a particular type of value. So it could be more like a set of users. So in this case now we are storing users here, but we are not storing them with an ID. You get? Now, yep, that's the major compact types we have in it. So at this point, I'm sure you've learned what primitive data types we have in compact, and we've also learned custom data types in compact. We've gone further to learn about mappings and sets in compact rather. So we're going to move to ledger states, what ledger states are and how to define ledger states. So for that, I'm going to create a new lesson 4, that's compact. And then I'm going to copy what we had here. Yep, it is here. Then let's paste it here. So I'm going to cut every other place. Now, what is a ledger state? Now, ledger states are or ledger state declarations are lines of code we write to kind of define what values we want to store on the blockchain ledger. What we want to store publicly. We want to be publicly available. You get? So those are what ledger states are. This is as more opposed to the privacy feature which Midnight allows us to kind of exhibit, where we can store data privately in a user's private state. So for ledger state, you define what you want to store publicly that is accessible by everyone, and everyone can also update the state of that particular variable. So think of it as a way of defining variables instead of saying just const, right? But there are ways to define a variable, but that is stored on chain. You get? Yeah. So to define a ledger state, you can do ledger, and then I'm going to take this out. Ledger, and then you write the name of the state. For instance, I could say maybe users, just as we've had in our previous example. And then this ledger state is a mapping. And it's a mapping that keeps track of each users. I'm going to quickly copy this from here. I'm going to copy all of this here. I'm going to copy them and bring them here so we can have access to them here. So here, I've brought all of our custom data types so we can use them here to define our ledger state. So we are saying we're defining a ledger state that's going to be stored on chain, a list of users that can be accessible by everyone and updated by anyone. And so it's going to be a mapping that contains maybe a user ID, which is of type bytes 32, to the user itself. I remember this user is a custom data type here, right? Making reference to each of these custom data types as well. So just by doing this, we've defined the ledger state. Now, to make a ledger state publicly accessible from the contract, you have to export it. So once you export it, your JavaScript dApp can actually utilize this particular variable, more like it's accessible outside of your code. You get. So that's how to define a ledger state. We can define maybe some more ledger states and define another ledger state. Say maybe for instance, counter. Now I can just call it maybe a uint 128, or I could use another data type called counter data type. This is a very specific, Compact specific data type provided to us by Compact as well. So counter, yeah. So these are examples of ledger state declaration. Yeah, these are examples of ledger state declaration. Now, one thing to know is once you've defined this particular data types as a ledger declaration, you now have access to a bunch of properties or methods that you can use to update this ledger state. For instance, for mappings, you have access to, you can actually do something like users.lookup. Now, this lookup allows you to be able to go through this user's ledger state, and then using a specific ID for that particular user, you can find a particular user in the mapping. You get. It can also give you access to a particular method called members that allows you to be able to check and say, okay, member. That allows you to be able to check and say, is this particular user with a particular ID part of the mapping? And lots of that. And also give you access to the size of that particular mapping. Similarly, for the counter, since I've defined a counter using this custom primitive data type here, I can do counter.increment and specify a number I want to increment by. So just so you know, if you defined a particular data type as a ledger state declaration, you have access to a few methods on them. And one thing to bear in mind is that data types like mapping, counter data types, the mapping and set are majorly called ADT data types. They are usually called ADT data types. Yeah, back to this. So these are how to define ledger states. Can keep on going to define maybe other ledger data types and data types. So ledger, let's say we want to keep track of an address on chain. I call this maybe a bytes 32. That's another ledger state. We can do another one. Say maybe ledger to keep track of let's say message, somebody's message. I can call this an opaque data type. So just trying to use all of the data types we've went through. We can actually do another one. Say maybe ledger state. Let's say admins. We have an admin for a smart contract. Then we can call this a set of admins represented by maybe the address got bytes 32 of type byte 32. Just like that. Maybe another one. I'd say ledger state of type is valid, for instance, just to express the booleans. I can call this a boolean ledger state. So you see, we can define this just like so, using all of these data types. We've talked about this. Let me see which other one we've not used. Yeah, we can go on to also say maybe want to define a fixed length array. Say puts, for instance. And then a fixed length array, if we're going to define a fixed length array, remember I said we can use vector data type and then specify, okay. So we specify the length of the array, maybe 10 foot, only a maximum of 10 foot, a maximum of 10 foot can be pushed into this particular array. So vector of 10, and then we specify the type, maybe bytes. I prefer using bytes. It's actually standard, more like industry standard for you to use bytes whenever you want to represent strings. Yeah. So this is it. You can keep going like that. You can also add a list data type. Maybe books, and then say lists, and then we'll call this a list of bytes. Maybe names of books we forget that. Sorry. So this is how to define ledger states. Now, what these ledger states share in common is they are publicly accessible on chain and can be read by anyone. Now, there's also a special way to define ledger states, and that's this. Let me just call this, and they are particularly called sealed ledger states. Sealed ledger states, and what sealed ledger states are is that they are ledger states that are declared. Their values are declared only at the point of deployment of the contract, which means when you are trying to deploy the contract, it's the only point where you can actually give a particular value to that specific ledger state. For example, now I can create a new ledger state called super admin. And with super admins should be defined by anyone, should be specified at the point of contract creation. So we know that, okay, this is the person that created the contract and it should not be changed. So this is the super admin. Now, to make this a sealed ledger state, what you just have to add here is sealed. So what this tells the compact compiler is this particular ledger state can only be given a value at the point of deployment. At the point of deployment, it cannot be specified. It cannot be changed. It cannot be mutated after that point. You get? So this brings us to the next topic we're going to be looking at, which is called constructors. So I'm going to create a new file. Lesson 5, compacts. So I'm going to copy all of what we had here, and then I'm going to bring them over here. So now, like I said, the sealed ledger states brings us to the next lesson called constructors. What are constructors, and how do we define a constructor in compacts? Now think of a constructor as more like a function. Let's just put it that way. It's best to call it a circuit, but since we've not talked about circuits, let me put it as a function that can only be called at the point of deployment, or that is called at the point of deployment, and it is used to initialize some states within the contract. A function that can be called at the point of deployment of a particular contract and is used to define, to initialize values for some specific contract state. So how do we define a constructor in compact? Simply do that by doing constructor. I'm going to clean this. So this is how you define a constructor. It's similar to what you have in TypeScript classes. So where you define a constructor, and that constructor is used to initialize specific values inside of that TypeScript class. So that's what they are here also in Compact. Now, which means just as we can do in TypeScript, constructors can take in they can actually take in a bunch of values that they will use to initialize the state. Maybe init, in our case, we have the super admin data types here. I can do init super admin, and this is going to be, it has to be of the same type, byte 32. I have to put, there's no need to put a comma here. So we can now call this super admins here. Remember I said sealed ledger state can only be declared once at the point of implement, and this is, they are usually defined within the constructor. If you do this, if you try to change the state outside this particular constructor, maybe in any other circuit, I'll call them functions for now. If you try to access to change them inside of any other circuit, you're going to get an error. So at this point, we can just call this init super admin. Now, one thing I'm going to try to do, just to give us a hint of how to check for errors in your compact code, is I'm going to try to compact this minimalistic contracts that we have here right now. So to do that, I'm going to go into my package.json and define a new script, and I'm going to call this compile. And then what this script does is it just calls compact C. If you follow the previous video on how to set up a compiler, you should be able to follow through with this. I'm going to call compact C, and then I'm going to call specify the name of the folder, the name of the compact file I want to compile. So I'm going to say compact C. It's inside of my source directory. So I'm going to say /src, and this is the one I want to compile. So I'm going to say lesson 05.compact. So this is the file I want to compile. And then I'm going to specify the folder I want to compile it into. So it's going to be /manage folder. So if this folder does not exist, it's going to try to create that folder and bundle all of our generated artifacts for the compiled contract into it. So /lesson 5 for our case. So this is where it's going to compile it. So what I can do now is I'm just going to try to call, let me bring this down a bit. So yes, I'm going to try calling npm compile. I'm just going to add run compile here. So now you can see this is how to check for errors. When you try compiling your compact code, you are going to get a bunch of error if it's not valid compact. So here it's in unbounded identifier list. So this is because of one error I've made throughout all of these files. After defining this language version here, the next thing you want to add for all your folders is to do import compact standard library. Now, this gives us access to all of these data types here that we can use. All of these ones you can see here, all of it. So I'm going to do this for other files. I'm going to go into other files, paste them here. Of course, we are not compiling them, but just for doing sake, we have it here as well. Okay, I'm going to paste it here. And then lastly here, which is the file we are currently in. So when I try to compile it, let's see what we get. Yes. So that error is gone now. It tells us this is the error I was trying to let us know, which was why I tried to compile the contract. So you can see what it's trying to say is the error we're getting here, it's occurring at line 34, which is this line here, which is this line of code. And then it's saying potential witness value disclosure must be declared, but it's not. Witness value potentially disclosed. The value of the parameter init of the constructor at line is line 32, character 5, nature of disclosure. What it's just trying to say here is whenever you are passing any value into your contract circuit, as I said, I'll call them functions for now, or into your constructor, you have to disclose them. Why is this so? This is because by default, Compact treats every value that is external to a circuit as private. So you have to explicitly disclose them. Compact puts privacy first and gives you more like it's privacy by default, and it gives you the ability to explicitly tell Compact whether you want that value to be disclosed or not. Now, I'm going to cut this out and I'm going to say disclose, and then going to paste that back. Now, what this does is I'm explicitly telling Compact to disclose this value within my constructor. So actually at this point, it's okay to disclose it here since it only occurs, it's only been disclosed within the circuit in itself. So do you get that's it. And if we try this now, we're not going to get that error again. You get now, you see, a new folder was generated for us. I misspelled managed, so it's supposed to be managed. The new folder was created for us. Let me delete this one. That update my file. So let me call it managed. And then I'm going to run compact compile again. So you can see it's compiled our code correctly. At this point, we are certain that we don't have any error. So you can see compact compiler. These are the artifacts it generated. So we're sure now that our code is compiling successfully. So whenever you want to check if what you're doing is valid, you can actually just do that. So you see, we now understand what sealed ledger states are here. There are ledger states that can be declared only at the point of the deployment. We also know what constructors are. They allow us to be able to initialize certain states within our contract at the point of deployment. So that's it for constructors. Moving on, let's look at circuits in Compact. Now, I'm going to create a new folder. Call it lesson 6.compact. So, what are circuits? What are circuits in Compact? Now, I do have an illustration for that. So let's look at that here. Now, in Compact, circuits are likened to functions. Just as in TypeScript, you have a function that you can call to carry out any task that you would not want to, and any task that can be used. Any piece of code, it's more like a block of code that can be used in several locations of your code. So that's what circuits are. But in the case of Compacts, they are not just functions, they are a mathematical representation of the program written inside of them. So this the program you write into them are being converted into a mathematical representation that can be either proven or verified. More like your code within your circuit are converted into a mathematical constraint. So whenever a user executes that circuit, whatever the output of that circuit is has to be in line with that mathematical constraint, which is going to tell the circuit if it is valid or not. Why is this so? This is because for compact or for midnight, it's designed such that your actual code is the actual contract code is executed off chain, and then only a proof of that transaction is what is being sent on chain to be validated. So for that reason, you see there's a need to check if a user has executed that circuit correctly, if they've not manipulated it. So this implies that at the point of deployment of that contract, you also have to also kind of in a way tell the blockchain that, okay, this is an instance of my contract that it can use to kind of check, of my compiled contract that it can use to kind of check against any other transactions that has been sent to the blockchain. So that's just what circuits are. Circuits are functions, but more than functions, they are being compiled into mathematical constraints that can be validated. So they can also be seen as entry points to the contract. They are functions that your users can call to update the contract state. So think of it here in our case. If we want to create a circuit here, a circuit could be created to add a new user to this mapping here, right? So we can say, okay, create a new circuit to export it, to make the circuit openly accessible for anyone, serve as an entry point for any user. We have to export it, say export circuit, and then you write the name of the circuit. In our case, let's say we want to go to circuit to add a new user, add user, and then we add this colon and tell it what it's returning. In our case, since we are not returning anything from the circuit, we're just going to put these square brackets here. So this, by defining this alone, we have a circuit. Just doing this alone, we have a circuit. If I try to compile this code and I run npm run compile, now see what happens. You can see that if I try to compile this code, so if I try to compile this circuit, I'm going to, since we are working on lesson compact 6 and lesson 6, so I'm going to change this here to lesson 6. Then I'm going to rename this to lesson 6 here, and then it's just going to add that particular folder inside of here. So what I'm going to try to do is run npm run compile again, and you can see we now have another folder indicating artifacts that are generated for this particular code here that we are currently editing. I'm going to close my terminal. So yeah, and if I open it, you can see we have an extra folder called zkir folder. Generally, it's going to I added this command here to skip generation of zk keys. So I'm going to try running npm run compile again. So you can see it's trying to compile that circuit. So it's going to compile that circuit, and then it's going to generate a pair of keys. So you can see here what it just generated. It generated a pair of keys for us, a prover key and a verifier key, right? The prover key and the verifier key. These are used to do all of the verification to see if a user has executed the circuit correctly. So you can see the name corresponds to the name of our circuit here. So if we have some other circuits, maybe I add, just going to add other ones. Say maybe add user 2, add user 3, and then I try to compile again. You're going to see that for every circuit, it tries to compile each of the circuits, and then it generates that prover and verifier key for each of them. So those are what zk circuits are. Now, a user is able to call this particular circuit to carry out the logic that is inside of it. Usually the logic inside of every circuit in a way updates the contract state. Now, any circuit that does not update contract states are called pure circuits, while those that update contract states are called impure circuits. So in this case, we have 3 pure circuits. If I'm going to add a pure circuit, the pure circuit is one, this is a ledger state because counter here is defined as a ledger state here. So if, for instance, say we have a new circuit that we call say hello, and this returns a byte 32, a byte 5, because the word hello is made up of 5 characters. I remember we said byte, so it just returns the string hello. And then if I try to compile this code, it's going to also generate that. I didn't export it, so it's not going to. You see, even if I exported it, it did not compile that particular circuit. This is simply because this circuit is not updating the contract state. Therefore, it's a pure circuit. It's only allowed to be used inside of this compact file, or maybe in any other compact file. We'll get to see how we can utilize pure circuits across compact files when we get to the modularization section of the course. So there are 2 types of circuits. That's what I want us to understand. There are impure circuits, those that modifies the contract state, the ledger state, and those that do not modify the ledger state, which are called pure circuits. So in our case, let's actually write logic to add a new user, so at least it's kind of more practical. So to add a new user, we can just say, okay, we take in a user property, a user parameter rather, and then this parameter, it has to be of this type because we want to insert that user into this mapping. We can collect a new user of this type here. Say, okay, this is our new user. And then what we can do is simply just insert that particular new user into this user's mapping here. What we can do is just say users as we've defined here. I'm just going to cut this out since we're not using them, so we can see clearly. So we're just going to add them to these users. So new users dot insert now, so okay, to add these users now, we need to remember this mapping is a map. It's a mapping of a user's ID to the actual user itself, which means we need an ID. So we can just assume that this user is giving us an ID. Our circuit is collecting an ID here as well, and the ID is of bytes 32. Yeah, and then we can use that here. So I can use this ID now and say, okay, insert this ID. It's going to give us an error, but I want you to also see the error as well, so you get to learn why we get the error in case you are writing your own compact code and you experience it. So ID, comma, and then the user. Now, if we try to compile this code, in as much as we are doing it correctly, we're going to get an error, and we are going to see why in a minute. If I try to compile again, now see, we get these 2 errors. And what are these errors? Both of them are pointing to the same line 32. So where's line 32? This is line 32, right? I'm going to zoom in a bit. Yep. We're going to take this down a bit so you can get to see. Now it's pointing to line 32, and this is it. It's saying, you are saying something similar to the error we had before, saying witness value disclosure must be declared. It's a witness value, and potentially disclose, which means we have to explicitly disclose that value. So what we can do is just say, okay, maybe const disclosed ID. Disclosed ID is equal to disclose. So this disclose is very important and it's used to disclose whatever witness value or parameter we are receiving in our circuit. So I can say, okay, disclose this ID. I can also do that for the user. Maybe I can just call this new user and say, okay, disclose user. And then I can, instead of putting them directly, since I've explicitly disclosed them, I can add them here and say, okay, here, disclosed ID. And then say new user. And at this point, if we try to recompile our contract, we're not going to get any error this time. So you see, our compact code compiles correctly, right? So you see, whenever you're using passing a new parameter or a witness in your circuit, you have to explicitly disclose them. Yeah. So insert method is one of the method, like I said, that is available on a mapping ledger state. So it allows you to add a new user to that particular pool. Now, one important thing you want to do is you might also want to check, for instance, if this user is already a part of this mapping, so we don't get to add users twice. Now, to do that, we can use the assert method. Now, what is assertions in compact? Assertions are more like if-else condition, but in the case whereby the condition is falsy, the entire circuit terminates and it reverts. Like it just terminates the circuit. It does not go further anymore. You know, when you have if-else, you can do, okay, if this, if that's not the case, now go to the else block. But in the case, once the condition is not true, which means for your code execution to move past this block, whatever is asked must be true before it can move. Otherwise, the circuit is just going to revert. And every state it has changed or whatever it's going to do, it has done before, it's going to revert. You get? So that's what assertions does. So in this case, what I can do is say, okay, users, we want to check our previous users and see if this particular new user is already part of the mapping, if they are previous member and they're just trying to trick our code. So we can say users.member and then disclose the ID. Right? So disclose the ID. And then, which means for it to pass down to add the new member, this condition must return true. If it returns false, it tells them this error message, maybe say, oops, you are not a new user. So if this condition does not return true, it's not going to go forward. The circuit is going to fail. Circuit execution is going to fail, and then it's going to return this message to the user. You get? So that's what assertions are for. So it's very important. You want to use this in your circuit as much as possible to avoid, to reduce gas cost and to prevent fraudulent manipulations of your circuits. You get? So that's what assertions are for. So we've learned, we went a bit extra since we're just getting started. We went a bit extra to add assertions. Hopefully you get what assertions are and you know how to insert a new object in the mapping. So we also have other methods, right? We also have lookup for mapping. I'm going to leave a link to the documentation where you can see all of these methods that are available for those ledger states, digital data types, like I call them. You come over here, you're going to see for mappings, and then you should be able to follow through. We also have insert. We have insert coin. We're going to learn more about them later on in the series. We have lookup and the rest of them. So we've learned what circuits are. We know what constructors are. We know what sealed ledger states are. We know how to define ledger state. We know custom ledger state, and we know data types in compact. If you've been able to follow up to this point of the course, you actually deserve a cup of coffee. Yeah. And moving on, we are going to move to another important component of midnight smart contracts, which are witnesses. Now, what are witnesses? Sorry, I'm going to reduce this a bit. I'm going to create a new folder, new file, particularly lesson 7, compact. Now, what are witnesses? I'm going to copy this. Yep. I'm going to copy what we have here into this file. Yes. So what are witnesses? Now, witnesses are in compact are a utility function. I'll put it that way, just so it's very understandable. They are a utility function that allows us to utilize off-chain data. Think of witnesses as oracles. I guess that's so complex. Okay, let's look at witnesses this way. Blockchains actually cannot interact with the normal Web2 environment, maybe with your normal JavaScript code by itself. Blockchains has its own environment, different from Web2. So usually for blockchains to be able to interact with off-chain data, maybe price data, you're building a DeFi protocol that needs price data and the likes of that, then you need off-chain data, right? The only way you can do that is through oracles. Oracles are more like this intermediary that allows you to fetch those data and pass them into your contract. Of course, we can think of witnesses in that way. Witnesses now are more like just more like a link that allows us to directly utilize off-chain data in our code. More like you can have a function, a JavaScript function that is executing outside of your compact code and then returning a value that you can use inside of your code. A function that is external to compact, maybe a JavaScript, a TypeScript function that you can use inside of your code. That's what witnesses allow you to do. Allow you to use off-chain data, private data. You get. So that's what witnesses have. Now, to define a witness, you do it this way. Say witness, and then the name of the witness. Witnesses, like I said, are usually functions that allows you to retrieve off-chain data and then use them inside of your code. So it could be maybe secret key, function that gets secret key, a user's secret key that is stored off-chain. And it returns the secret key, let's say it's a byte 32. So this witness is going to have an off-chain implementation of this code that it then uses to retrieve that particular data and send it into our code. So for instance, let's just say it's not the ideal thing to do, right? But instead of this guy here that we are using as our ID, I'm going to take this out. And then we can use our witness instead. Assuming we had a way of, let's even call it get ID, get user, or let's say generate user ID. Generate user ID. And what it does is a function that just generates a random user ID and gives that to us. So what we can do now, instead of using this disclosed ID here, I say const new user ID is equal to we have to, it's a witness function, so we have to disclose it. Whatever value it returns to us is a witness. We have to explicitly disclose it. So, I'm going to disclose what we have here, what this guy gives us. I'm going to call that function here. I'm saying disclose generate user ID, and I'm calling the function. So I'm calling the witness function. The witness function is going to retrieve the randomly generated ID and then return that to us. Then I'm disclosing the value and then setting it to become my new user ID. Now, one thing you must have noticed, which I didn't state, is the fact that I'm using const to define the variables within my contract. Yeah, it's allowed, since this is one of the reasons why people say compact is a lot similar to TypeScript, because it feels like TypeScript. You're using const to define variables inside of your contract, but you can't use const to define ledger states. That's just so very clear. Ledger states are different from just circuit variables. You can use const here, and you cannot use let inside of the circuit, importantly. So, it's kind of trying to stick to the immutability concept of the contract. In smart contracts, the logics are immutable. Also, in TypeScript, constants are immutable, which means once you define that variable, it has been defined. It has a specific reference point in memory and cannot be changed. Cannot be overridden. So that's the essence of using const here. So going down, now we've been able to use we're utilizing our witness function here that helps us generate a new user ID, and then we are then using the return value here, and we are disclosing it and setting that to become our new user ID. Now, instead of using this disclose ID here, I'm just going to auto select both of them. We can use our new user ID. So, like we can see here, if we compile this code, it still works. Let's see. Fine and good, it compiles correctly. If I fail to disclose this value, it's not going to work. I try to do that. Let's see. Oh, it worked. It worked. But usually, it's much more ideal that you explicitly disclose witness values where they are needed, right? Oh, okay, it's even making reference to the previous code. That's why I'm going to change that here. So compacts, lesson 7. Lesson 7. It's not going to compile. Let's see. So I try to compile again. You can see I get the error saying witness, you get disclosure, and it's pointing to everywhere I'm using it. So if you get the errors, this same error pointing to the same line, you most certainly just want to look at that line. And once you fix it, it's going to take effect in other places where that witness is used. If I revert back to what I had before, where I'm disclosing it, and then I run compacts compile, you can see it compiles correctly now, and it's compiling the correct compact code now. So this is how witnesses are. Now, we've only seen the on-chain representation of witnesses, how to use them. But remember we said there are functions that are implemented off-chain that returns a particular value that can be used inside of our compact code. So how do we define them? So let's see how to define witnesses off-chain. So to do that, I'm going to create a new file called witnesses. Compact .ts, sorry. So inside of this witness file, what this allows us to do is we define a constant called witnesses rather, and it's an object. Now what this takes is it defines a bunch of functions that are directly similar to what we define inside of our compact code. In this case, we had this function, so that's what we're going to define here as well. And come back here and say generate user ID, and then this is my function, right? So whatever I implement into this is what is going to return to me is as the result of this witness function that I can use on chain. But it's not complete this way. We also have to do some extra work here. Yeah. So we have to define our private state here. Usually witnesses is assumed to work with private states, even though at some point, some of your witnesses might not even actually update private state, but your witness value has to always return the current instance of your private state. So the contract has a way of tracking how the current state of the user's private state. So I'm going to create a new instance of user's private state and say, let's just call it what we're writing is simple user contract, right? Let me call it here user private state. This is TypeScript. I'm sure at this point when you're trying to learn Compact, you already know TypeScript, so it's going to be a lot easier for you. Interface. I'm going to define a new interface. It's just an empty user private state, right? At this point. Now, this we have to give witness circuit, a witness function rather, the context of the contract. So I'm going to call it context. And then how do we get this context? One thing to notice, like we saw here, for every version of our compiled code, we had a bunch of files. These are the files that are generated. And then if you look at this here, if you look at this particular contract folder, we've not talked about what are inside each of these folders aside from the keys folder, where we saw the prover and verifier key pairs. So if we open this compiler, we're going to say contract info.json. This allows us these kinds of define everything that we have inside of our contract. As you can see, we also have a circuit here, add circuit, which represents what's the kind of circuit we defined. It's telling us arguments, users, which is what we defined, type name struct, which is what we defined, as you can see inside of our contracts here, right? Yeah, as you can see here. So now this allows for compact composability. This is not our consign. Our consign here is this folder, this contract folder. This contract folder usually compiles and contains a TypeScript compiled version of our code. Now, if you go through this index.js file, if you go through this index.js file, it's going to tell us, you can see it's a representation of our code. You can see these users, except that it has a very strange look compared to what we defined. You can see it's telling us contract, telling us witness, and this witness, you can see it's telling us this is a circuit. It's more like a class, a contract class. We have users circuit. You can see it here, and you go down, just a bunch of gibberish that is a compiled version of our code. This actually is similar to our compiled code. Now, this I'm trying to point particularly at a particular portion of the code. I think it's here. Yes, witnesses. This one makes witness and witness context. It gives us the direct representation of the witnesses that our contract code uses. So if I come back to our witness, what I can do is I can define the type of this context to be witness context. Sorry. So I can import from at I have to import a particular type helper from a specific midnight library, which we'll have to install. You can see that was what it was making reference to here. This library that it cannot find. So I have to install this. I'm going to copy it and just paste it here and say, okay, npm I this particular version is it's going to try to install the compiler, the compact runtime rather, sorry. So let's see. You can check here to see what it installed. This is not going to work because we are working on the preview testnet and it uses a specific version that is currently a release candidate, but it's not actually public. So I'm going to just copy that from one of my other project folders. Let's see. I'm going to copy it from here. Yeah, this is a particular version of the compiler I want to install. So I'm going to hit enter and have it install that particular version. Now it has installed it. If I come over here, I can see that it's now in my dependencies and install that particular version. If you come back here, we're not getting the same error we were getting just of recent. And then we can import from that particular package shell. So midnight compact runtime. So I'm going to use import witness context. If I hover over this, you're going to see what it does. The external information accessible from the compact witness core. That is what this type defines. So it takes in two parameters. You can see it takes in two parameters, the ledger type and the private state type. Both of them are of any type. So let's do that. So it takes in it's a generic type that takes in two parameters. Ledger type. This ledger type can be imported from our contracts that we just compiled. So if I can see it's importing from manage/lessons/compact contract, and we're importing the ledger type. You can see what it's giving us access to. The user ledger state, because that's the only ledger state we have defined, and also, the super admin ledger state. These are the two ledger states that we have defined. Come back here, you can notice that we only have this guy and this guy. I'm just going to move this guy up here a bit. Okay, so back to this. Now, we've passed one of the parameters that is required for this generic. We also have to pass our user private state, right? So, and like I said, every witness function has to return two things. It has to return first the current state of the user's private state. So yeah, it has to return user private state, right? Current state. And then it has to return the particular value that it is returning to the compact code that it's going to utilize. In our case, it's a byte, right? What we defined here is by saying this witness function, when it's called, it generates a random user ID, returns the ID, which is the byte 32. But unfortunately in TypeScript, we don't have bytes. So an equivalent of bytes would be a uint 8 array. If you're finding it difficult to understand this, there's a documentation for this that tells you what each of these particular contract types are similar to in TypeScript. I think it's here. Okay, you can see here. It says Boolean equivalent to Boolean in TypeScript. Build is equivalent to bigint, uint, and purpose. You can see bytes is equivalent to uint array. So this is how I know that we can use uint 8 array to represent the byte. So we're saying, okay, it's going to return bytes, but in this case, it's using uint 8 array. So, which means I have to complete our function, return this. That's why we're getting this red squiggly line. And then what we can do is Now say, okay, we want to generate a random user ID. To do that, I can call it, let me just say, user ID, and then it's going to be a new int array, int array, and of length 32. Since it's of byte 32, so we also want to return a int array of length 32. And then what we want to do is, we're just defining an empty int array of byte 32. So we want to fill that particular array with just random values. So what I can do is create tool. This is a native Node.js global variable that I can call to get random values. So I can say get random values, and I can pass the array I want it to fill inside of it, which is our user ID. And then it's going to fill that. Then I can return this user ID or this now a random int array. What I can do now is say, okay, return. To fulfill this condition here, I have to return array that contains our private state. So in this case, we didn't make any changes to our private state. We're just going to do context dot, you can see, private state. We also have access to, which means within our witness functions, we can access our ledger state as well. I'm going to show that in a bit. So I'm going to return private state, then comma, this value is our user ID, the random user ID we are generating. Maybe to be more clear, I'm just going to limit to random user ID. So it's generating the random user ID and returning the current state of the user's private state, which has not changed in our case, and value is sent return. The contract is going to read these two values. It's already going to utilize this by itself, but what is more important to the contract at the point where we are calling that circuit is this. So this is what it's going to fetch and give our contracts to use within its own circuit. So yeah, that's majorly it. So just to expand on this, I was saying that we can access our contracts, our ledger state from here and actually read the values. You can see and say context of ledger state dot users. And then we should be able to also look up here. So you see how powerful witnesses can be. You can utilize witnesses to carry out calculations off-chain, maybe calculate a specific value, and then return that value to through the witness back to the function. In our case, we're generating a random ID and returning it back to our circuit for utilization. So this is how witnesses are. Now, just for conclusion, I'm going to state it again so it's clear, because I know this was one point I found much more difficult when I was trying to learn. Witnesses are functions that are implemented off-chain that either returns, carries out certain calculation off-chain or updates the user's private state and then return the latest value to the contract. Yes. So that's what witnesses are. Off-chain functions. Off-chain functions that can be utilized inside of our compact. Then, like I said, defining witnesses just like this and utilizing them wherever we want to is not enough. You also have to define the functions, implement the actual functions in itself in a separate witness.ts file. You have to use this because this is the only way Compact will be able to identify this is the naming convention. It's going to be identified that, okay, this is the witness file to use. So, yeah, it's, you have to also define the function, implementation of the function outside, and then always return it in this manner on the private state and the return value that you want to utilize inside of your function. I'm going to quickly export the first here. Witnesses. This at any point, if any of this is not correct, it's not clear, if you to ask in the comment section. And This is subject to change maybe in the future. But at the point of recording this video, this is how we necessarily are done. If you have any questions, you can also join the Midnight Discord channel. I'm going to drop a link to it in the Midnight, in the description of this video, and you can ask your questions there. And also hit me up personally on Twitter, on X rather, or on Discord as well, or on LinkedIn. Then I'll be ready to answer the question. Now, moving on, we've discussed about weaknesses. We're going to move on to modules in Compact. Now, this is one of the most fun aspects for me in Compact. What are modules? Like we already know in languages like TypeScript and Node.js particularly, Node.js. Now, for Node.js, you can define you can split your code into smaller chunks that can be imported or exported or used by other files. So similarly, we can do stuff like that in Node.js. For instance, I could create a new file that stores only my custom types. Yeah. I can create a new file here. I call it maybe custom types dot compact. It even allows us to create our own custom library. In the case here, we see we have compact and a library. We can also create our own custom library here. Let me call it custom library. Yeah. Custom library. Sorry. Compact. Then hit it. Now, doing this alone is not enough. You have to define a module in a specific way. You say module by this. This is my extension helping me out. So you have to name it exactly as you name this file for easy importation, or I'm going to show you both ways of importing it. So we're going to call it custom library as well, just as I named the file. Okay, I'm sure that is correct. Yeah, it's correct. Now, for modules, you don't have to specify this pragma version like we did here. Doing it here in the main compact file is enough cover for all. What we just need is this guy here to be able to also use this compact special library primitive types as well. So I'm going to come back to my compact custom library module. Then I'm going to paste this library here. I'm also importing all my primitive data types so I can use them here. Now, what I can do as well is copy all of this. Maybe I want to kind of make my file more readable and cut all of these custom types, cut them, bring them here, and paste them here. So I'm just going to format it a bit. Yeah. So, yep. Now, what you want to do is for them to be accessible outside of this module, you want to export them. Click on export. Just going to select both of them as once. Export. You can do it this way, or you can add an export field here. Say export, and then you list all of the variables you want to export. So you just do maybe in this case marital status, address, and then user. So in this case, in both cases, we're exporting all of these variables outside of this mode. And once we've exported them, it means we can now import this particular module inside of our main compact file. What I can do now is import custom library directly. So I'm importing it directly here. And it works like this simply because if I try compiling the code, right? If I try compiling the code, I should not get an error. I'm going to try compiling the code. Yeah. So you notice I didn't get an error. So it's still able, this main compact file is still able to access all of those types. It's able to access these user types that is being defined inside of this file. This is what modularization helps us to do. It helps us to better structure our code so that we don't have just one file where everything is just jam-packed in one particular file and it's becoming too long. What I would actually call spaghetti code. So we have all of those custom types separately, and now our code looks a lot cleaner. Yeah. Another way is if we decide not to use the same name here, of course this is best practice. But if we decide not to use another name, we call it types, custom types, as opposed to custom libraries here. What we can do is say what we can do here is just say import / custom library. Let's try compiling and see custom library. Let's compact. Let's try compiling to see. Okay, we added compact twice, so it's no longer. So we're going to try compiling again. So you can see the error is showing between /this defines custom type module this rather than this. So you get it's not going to work this way. So you always want to name your module in itself same as the name of the file, so you can utilize it. This can change later on, but for now, this is how it works. So if I leave it the same way, try compiling again after changing the name of the module back to compile library and see it's going to compile successfully. And see it's going to compile successfully. And another thing you can do is you can also prefix a name to all of the chunks of code that your module imports here. Maybe I can call it custom type here. Custom types. Maybe like this. And then I call this like this. Instead of directly using users, I'm going to have to add these custom types before the users. So here as well, I'm going to add custom users here as well. So if I try to do this without adding custom users, the custom types after prefixing it here, I'm going to get an error. If I try to do this without that, let's see. Tells us bounded identifier because we prefixed all the imports that we're importing from this module here. All of it, we prefixed it to with this particular namespace. So we have to always add it to use it. And one thing to note is that this particular namespace format that we added is only restricted to this file. Any other files that imports it as custom library directly and does not prefix it will be able to use them directly without having to add this namespace that we just added. I try compiling now. Sorry. Okay. If I try compiling up, and boom, we have our contract code compiling just as expected again. So that's the most formal modularization. So just a recap. Modularization helps us to better structure our code neatly, and allows us to better structure our code neatly, and then allows importing codes wherever they are needed. Another suitable scenario you might want to use modus for is, say for instance, you have some global states that will be accessible. You want to be accessible by several other modules. You can create a global state module and then import them wherever they are needed and locate them whichever way you like. So that's one use case for module. Hopefully you got the benefit of this session. It's very, very important to help you write neat compact code. I've seen a lot of developers write compact code and you just have the whole thing in a single file, making it a lot much more stressful to read. And I think doing this kinds of places you ahead of other developers. And now, lastly, we move to compact standard library circuits that are important that Midnight has given us. Okay, so let's see. Now, there are a bunch of, I'm just going to do that finish here. Circuits from compact standard library. And use cases. Now, there are a variety of circuits that Midnight gives us through the compact standard library, and a lot of them. But we're going to be going through just a handful of them, since these are the ones I think are most important. And I'm not just saying out of thoughts, but I've used them in a whole lot of protocols that I've written using compact. So one of it is receive shielded. Now, this function was formerly called receive in testnet 2, but now it's called receive shielded. What receive shielded does is it allows you to receive any token, any UTXO input, token input that is coming inside of your contract. That's what the receive shielded is used for. Another one is send. I think it's send shielded now. I think it's send shielded. So it allows you to send token from your contract to a specific contract address or to a specific user. So that's what the send is for. We have send immediate. Send immediate. Send immediate allows you to send UTXO. Okay. Let's kind of differentiate both of them. Essentially, it allows you to send a token that is already existing on the ledger. And that is called a qualified coin info. Qualified coin info. That's previously now called qualified shielded coin info. And it's used to represent a specific coin that is already existing on the ledger at a particular Merkle tree index. But the send immediate allows you to send a coin that is being passed your contract immediately as it just enters. You can send it out to a particular user or a contract. So that's what send immediate does. We also have evolve nonce. Now, the evolve nonce function circuit allows you to generate new nonce, especially when you are trying to mint tokens to users. Another one is persistent hash. These ones are very crucial for hashing. Persistent hash. Persistent hash allows you to hash a particular an array of data. Particularly, maybe you want to create a hash for a particular user, maybe using a specific domain, a specific item, maybe the ID, merge them together to create a hash. That's what persistent hash is used for. Also have persistent commit, which is mostly used together with merge, which is also similar to the hash, but allows you to just hash a particular whole data, not necessarily an array. It allows you to hash specific data of a specific type. And then we also have what's this called? We also have unshielded. Now, unshielded is a circuit when called returns a burner address. And what are burner addresses? Burner addresses are addresses that when you send token to, they cannot be retrieved. That token is considered no more existence. That's what unshielded does for us. We also have many other compact standard library circuits, and you can as well explore them in the docs. I'll leave a link to it in the docs. So over here, and click on detailed API reference. I see there's a lot of them listed here. Including mint token to mint a new token to a user. Of course, this makes reference to the previous testnet too, but a lot has changed, and I'm sure the docs will be updated soon. Yeah, will be updated soon. And yeah, you can explore these docs. That's the majority of the things we need to know for this particular video in this series. In the next video, we'll go into how to handle liquidity of funds in our smart contract. Here we'll talk about how to receive tokens, how to utilize most of these circuits we've talked about, how to receive tokens, how to send tokens, how to store tokens within our contract, and how to manage tokens entirely in our contracts. Yeah. So thank you. See you in the next video. Be sure to like, subscribe, and give this video a thumbs up.